Okay, so the trajectory tracking control is basically we are trying to get a manipulator to follow a trajectory. So let's say that this is the Q. We just do this Q ref. The question is, can you get the manipulator to go on this Q actual? Okay, and so far what we have done is we have ignored the dynamics totally. We've always used MuJoForward, which doesn't do dynamics. So we need to use MuJStep, which I'll talk about. We've used MuJStep in dynamics, but we've not really used it for anything other than getting the dynamics. So I'll show you how to do this control at the end of this, but really we will try to track a reference which we generated in the previous class, right? Generation. So the Euler-Lagrange equations for manipulator look like this. Nothing new here. It can be shown that these equations can be reduced to this form. This form is very important, as we'll see for control. There's a mass matrix. There is a Coriolis term. There's a gravity term. The mass matrix depends only on Q, very important. The Coriolis term depends on Q dot, and the gravity term only depends on Q. I actually used this fact to get the equations M, C, G in an earlier class. So what we do here is we take this equation and we write it as A Q double dot equals B, where Q double dot is this Q double dot. We need to solve for Q double dot, all the acceleration. So A is M and B is all this thing. And then we can actually integrate the equations to get the trajectory of the robot or the joints. Now there are two objectives of control. One thing is a set point control. So imagine a pendulum, it's in the vertically downward position, and we want to get it to upright, or a set point of theta equals 0. So that is actually a benchmark problem. It's called balancing a stick. So that's one type of problem we are interested in. The second one, which we're driving towards in a manipulator in an industrial setting, is we want to do trajectory tracking control. That is, we want the manipulator to track, let's say, a curve, or we want it to pick and place like this. We have looked at joint space and Cartesian space trajectory generation. We can track in both those spaces. So clearly that first one, the set point control, is a special case of trajectory tracking control, because in a set point control, you only give the initial and final position, while trajectory tracking, you give the trajectory along the paths, right? So you could just ignore everything between the path and just give the start and the end, and then it'll just use some kind of a set point control to do that. It'll actually lead to kind of jerky motion if you're not careful. Okay, so we'll not really do set point control because we're not doing a controls class. This is basically a robotics class where we are interested in trajectories, where robots are doing something useful. And set point control, if you want things to go so fast, it can be very unsafe too, right? So let's focus on trajectory tracking. I want to motivate how control works with this very simple example. So this is the equation of a manipulator from the Euler-Lagrange. I'm going to reduce this to a very simple case where M is a constant. It's actually a number. C is a number. CQ dot, in fact. So it's still a function of Q dot. And then G as KQ. So it's like a spring. And the torque is force. So this is basically a spring mass damper, something which you've seen all the time. So the model or the figure for that is shown here, right? Now let's assume that F is 0. Okay, no force. So if there's no force, and if you take a mass and you pull it to the right by a small distance, let it go, it just goes bobs back and forth, right? So that's a free vibration of the system. So you can write an equation for, basically equation for Q double dot. There are two numbers associated with this. One is the natural frequency, that's square root K by M. And then there is something called a damping factor. This is called psi, actually, if you, in Greek, right? The psi, 2 psi omega n is C divided by M. So there are two parameters here. looks like there are three, right? K, C, and M, but you can non-dimensionalize them by dividing by M. So really two parameters. And those two parameters are basically those, the different way of parameterizing the same equation. Natural frequency and damping, psi. Okay, so this is a formula for omega n only in terms of system parameters. And this is a formula for psi, the damping, only in terms of system parameters. Okay, now that we have that, this is something you might have studied a long time back, which is there is, depending on the damping, which is basically a number which could be less than or greater than 1 or equal to 1, you get three cases. You have over-damped system, where the damping ratio is greater than 1. You have critically damped system, where the ratio is equal to 1, and then under-damped, which is less than 1. What these ratios mean can be illustrated by a plot of joint angles as a function of time. We subject the system to the same initial condition. So we set this, the mass at a distance of q0 from the 0 position. So 0 position where it does not move. So we set it and let it go. Depending on the damping, you will see different responses. If you have the first one over-damped, the blue one, you'll see that it follows this kind of pattern. It gets to time t equals, sorry, it goes to q equals 0, but takes quite a bit of time. If it's under-damped, the red one, it vibrates between 0 up and down, eventually reaching approximately 0. And then the critical damped one equals 1 goes to 0 in the shortest amount of time. So key is the shortest amount of time is taken by critically damped. Okay. Now this is free vibrations. This is a system where you've designed the damper, or in this case, designed C, K, and M, and you have no control over those things because you've designed them. And if you want to make it critically damped, you need to change the damping. But you can do more with control. Because you have F now in the system, you can actually tune the damping and spring constant. So what we'll do is, since we have full control over F, we will design F such that the system is always critically damped, no matter what M, C, and K is. So let's assume that we have a controller of this form, Kp times Q, Kd times Q dot. This is known as a proportional derivative controller. Proportional because it's proportional to the joint angles. Actually, there is a Q minus 0. I'm ignoring the 0 because 0 is a set point, but you could also do it some different set point. And then there is the derivative part is because you also take feedback from this sensor. So you need, for anything like this to work, you need sensors. In this case, you need sensors for Q and Q dot. You need to measure Q and Q dot. Okay, so let's take that F equals minus KPQ minus KDQ dot, sub it in this equation to get this equation. So just subbing in F. I'm going to club things together. So here I've clubbed C plus KD and K plus KP. And now it looks very much like a free vibrations equation, right? The force is 0. Now, of course, force is not 0. We substitute something, but it looks like a free vibration paradigm. So we could now use this fact that we want to design or choose KP and KD such that system is critically damped. Okay, critically damped means the damping factor equal to 1. Okay, and so that equation, if you see here, it's basically C equals 2 square root Km. So okay, here C is basically this, because this equation has not only C plus KD, so that is that, and then K is K plus KP, and then M is M. Okay, so we have to satisfy this equation, for the system to be critically damped. There are two parameters which we can choose. Remember, we chose Kp and Kd. So we have two parameters, two constants, and we have only one equation, which means that we have some freedom in choosing one parameter. So what you can do is fix one parameter and compute the second one because we have only one equation. So here we can fix Kp and solve for Kd. So if you fix Kp, so let's take this equation, fix Kp and solve for Kd, you will get just show you how you get this. So we have C plus Kd equals 2 square root K plus Kp. So when you square the two sides, you get C plus Kd square equals 4 mk plus mkp, and then c square. So you basically get a quadratic equation, kd square minus 2c kd plus c square minus 4 mk minus 4 m kp equals 0. And then two roots, choose the positive root. Now there is a condition that Kp and Kd has to be greater than 0, because otherwise you get negative feedback, which is positive feedback, which is not good, makes the system unstable. So you choose the positive root, and the positive root is this one. And this basically ensures the system is critically damped. No matter what you do, how much you pull it, it's always going to go to t equals 0 in the fastest time. Okay, now that we've got this condition on Kd, and we did it for a single degree of freedom system, a spring mass damper, in fact, that we did it for a spring mass damper. The question is, we want to take this to a manipulator which has multiple degrees of freedom. So how do you do that? So here is how you could do that. So extend idea to 2D. So let's say this is 1D. This is something which we've figured out. We've done that. Now let's do 2D. Okay, I'm just going to take the same equations. They don't have non-linearities, but let's just be with me over here. So I'm going to make this a 2 cross 2 matrix. So you can see that this is what it looks like. We design F equals minus KPQ minus KDQ dot. So I just put this. So you have, for KP, you'll have 4 numbers. For KD, you'll have 4 numbers. You have 8 parameters. Now you need to choose critical damping. Okay, there'll be 2 equations. And then why you'll have 2 equations? Because you have 2 modes, Q1 and Q2, which need to be critically damped. So there'll be 2 conditions. But you have 8 parameters there, 4 for Kp, 4 for Kd. So it means that 8 constants minus 2 constraints, equations, it means that you'll have 6 free parameters, 6 things you can choose. Okay, it's going to be way too many. And this is just for 2 degree of freedom. If you have a 6 degree of freedom, it's going to be a mess. You just have 3 equations, 6 conditions, but you'll have a lot many parameters. So this is not a good way of designing a controller. Okay, and remember, our goal is to get to 0 at the fastest time, because what we care is, can we get to a track or can we get to a set point? Okay, so what is done is this thing called inverse dynamics control. The idea here is as follows. The dynamics are given by this equation, same thing I wrote down as earlier. The goal is to track a reference, QR, 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 double dot. So this comes from trajectory generation using, say, quintic polynomials or cubic splines. The inverse dynamics controller chooses a torque of this form. This is very important. There's a mass matrix. Then we take the reference acceleration. Then we take Kd times the difference, this should be a dot, plus Kp Qr minus Q. And then so remember that this bracket closes here. Is important. Okay, it closes. And then we have C QQ dot plus GQ. Okay, so this form, why we use this form is because we'll see that it lets us choose very few parameters, not as many as we'd seen earlier, like so 6 parameters for 2D. So what we'll do is we'll take 2 and substitute in 1. So here is the left-hand side, M CG. This is 2. And then the right side, so this is 1. And then the torque is given by this. So this is substitution on the right side for the torque. Okay, so if you do the math here, the CG cancels off. You can factor out the M. You get an equation which looks like this. Let's assume that the error is the difference between the reference minus Q, right? That's what you want. You want the error, which is the reference, be equal to the actual joint position. So this is reference actual joint angle. And you want those to be mirrored, right? So the error is 0. So I wrote down this equation now as only in terms of error double dot, error dot, and E. And then the Kp and Kd are there. Now, I've not told you what Kp and Kd is as of now, but I will show you now what Kp, Kd can be chosen to be. So here is what you do. Because the mass matrix is not 0, you can check that. Unless, of course, you have one of the terms has 0 mass matrix is never 0. You can write the second part has to be equal to 0. We'll actually choose Kp and Kd to be diagonal matrices. So only diagonal terms. Everything else is 0. All zeros. Okay, in other words, you could write them as n equations which are all decoupled. So this one only has Q1 reference minus Q1, Q2 reference minus Q2, and so on till Q n reference minus Q n. Okay, now we can use what we've done for a single link manipulator or single spring mass damper, which is if each of those equations we want them to be 0, we can now use the critical damping equation. So the critical damping equation becomes even more simple for this because the mass matrix is 1, and then Kp and Kd is Kd1, Kp1. So here is the equation. I just wrote it down for with an index I. I goes from 1 to n. We compare it against the spring mass damper equation. I wrote the one with the free, the one with the free vibration with the control. So M, C, K is 0. M is here. That's 1. C, you can see it's 0. K is 0. And then for critical damping, Kd equals minus C plus 2 square root K plus Kp times M. And so we just get this really, really simple expression. Kd is 2 square root Kp. Okay, so to summarize, what you need to do is to use the inverse dynamics controller, you need to take this equation, substitute this very special formula. This is a very important step. If you don't do it, you'll not get what you are after. And then once you put that, you only need to choose fix Kp and then choose Kd by this, and it will be critically damped. Okay, with that, so this is the inverse. This is a summary of the inverse dynamics controller. Now there's going to be a problem with this controller, and I'll tell you what the problem is. So when you use this controller, as you can see, it needs M, C, G, which is here M, C, and G. How do you get M? Well, this Q, the sensor measurements are Q and Q dot, right? This is the actual velocity and the actual position of the joint. Joint position, velocity. So you need to measure those and then feed them into the controller. And the problem is that there are two issues which I think can affect them. There are obviously more. One is that the sensors are noisy. So Q will not be a smooth thing. It will be fluctuating. And then there could be a case because the way you set up the control system, there could be a delay in measurements, which means that Q is not what it is right now. It was what it was 20, 30, 40 milliseconds ago. So both those problems are going to affect your control. So what is done is this gets us to the next controller called feed-forward feedback control. What this control does is that it replaces M, C, and G with the reference values. Reference QR, QR dot. Okay, now what is QR, QR dot? These are computed from your, I don't know, let's say quintic polynomial. Okay, so if it's computed from a quintic polynomial, you don't really have to wait on sensor measurements. The only sensor measurements you need here are these. Not the M, C, and G, which is here you need all the measurements. So this is called feed forward and feedback control. The feed forward comes because this signal, you're feeding it, assuming that at that point, QR is Q. That's the feed forward part. The feedback part is because of this error, which is fed back.